Kothari, who is going to speak about no quantum speedup over gradient descent for non-smooth convex optimization. And the floor is yours.
Thanks, András. Thanks to the organizers for inviting me. All right, so I'm going to talk about, can quantum computers speed up gradient descent? Please feel free to ask questions during or after the talk. And this is joint work with Ankit, who's a researcher at Microsoft Research India, Praneeth, who was a researcher at Microsoft Research India while this work was done, and now is at Google Research, and Suhail, who is an intern at Microsoft Research and is a PhD student at the Tata Institute of Fundamental Research. Okay, so let's start with some motivation. So the first couple of slides are just going to be a little story about why you might care about this problem, but on slide 4 or so, I'll just state the formal problem, and if you don't care about the story, you can pick up again there. So what's going on here is we're interested in gradient descent. Gradient descent is this algorithm for minimizing functions in Rn. So you have a multivariate function, takes an n variable, spits out one real number, and you want to minimize this function over some domain. And it's a very popular algorithm in practice. And it's used both as a heuristic, so where we cannot prove provable convergence guarantees. So for example, for training neural networks, it's used all over the place in machine learning. And it's also proved in settings where you can prove stuff, such as in convex optimization. And my talk's going to be about this latter setting, about convex optimization. And the algorithm is very simple. In fact, I think the algorithm was proposed in 1847, so a very long time ago. And yeah, so let me just explain what the algorithm is with a very simple picture. So you're trying to minimize a function. So let's take a univariate function, so y equals f of x. And let's say you start at this point x0, and you're trying to minimize the function. You have only two directions to go in, left or right. And which direction should you go in? Well, you can compute the derivative at that point, x0, and you should go in the direction of the descending direction, right? It kind of seems obvious, like why would you go left? And you take a step in that direction, and you get to this point x1, and you do the same thing. And in this picture, at least, it's clear that you'll get to the minimum, or you'll get to a minimum. And this is the idea of gradient descent. So of course, there's also one variable example, but in the multivariable case, you compute the gradient at a point and take one step in the negative direction of the gradient. So like very formally, this is what the algorithm iteration step looks like. If you're at point xi, you compute the gradient at point xi and take a small step in the direction of minus the gradient, and the step size is eta. This is a parameter you have to choose. And yeah, for completeness, the gradient of a function at point x is defined as this thing. It's the vector of partial derivatives in each of the directions. Technically, the function needs to be differentiable for this, but you can naturally get around this, and I'll say something about this later. Okay, so that's just what gradient descent does. That's the basic gradient descent algorithm. Okay, very intuitive, very popular, cool. Okay, so then we ask the question, can quantum computers speed up this algorithm, right? This algorithm is very popular, so it would be great if we can speed this up. And immediately, if you think about this for a little while, you're met with the question, well, what does this really mean, right? What does it mean for a quantum computer to speed up an algorithm, right? So for example, does Shor's algorithm speed up the best classical algorithm for factoring? Yeah, probably not. Like these algorithms look nothing alike. Like the best classical algorithm for factoring doesn't look like Shor's algorithm. In general, it's not totally clear what it means to say, can you speed up gradient descent, or can you speed up a particular algorithm? You could try to formalize this question in some not very helpful ways. So here's one formalization that I don't like, which is where you would say that the quantum algorithm which speeds up gradient descent should do basically exactly what gradient descent does. It should output the same sequence of points, x0, x1, x2, and so on, that gradient descent would have had you run gradient descent on your input. But this is too much, right? Like you're asking the quantum algorithm to do too much. So that's not a great way to formalize the question. But what is meaningful is to say that you can fix some problem, say problem X, and say quantum computers solve this problem faster than gradient descent solves the problem. And so what we do is we choose to formalize the question as follows. We say, consider some problem that can be solved by gradient descent. And furthermore, this is really important, a problem for which gradient descent is the optimal classical algorithm, because otherwise even classical algorithms could do better than gradient descent. So somehow you want a problem that that truly captures the power of gradient descent. So it's a problem for which gradient descent is the best classical algorithm to run. And then we can ask, can quantum computers solve this problem faster? So this is just one way of formalizing the problem. There could be others, but this is our story to motivate this problem. And as I'll show you in a couple of slides, the problem is just very natural. So even if you don't buy this story, the problem is independently well motivated. Okay, so let me tell you what this problem is. So to tell you what this problem is, I just have to give you a brief intro to convex optimization. So convex optimization is this field, studies optimization problems of a special type where you're trying to minimize a convex function over a convex set. And most people probably know what these things mean, but here's just a couple of pictures showing what a convex function is. A convex function is a function where if you draw a line segment between 2 points on the function, the line segment lies above the function. And so here's some examples of functions that are and are not convex. And a convex set is a set where if you take a line segment in the set, then every point on the line segment is also in the set. Okay, and in this problem, I'm going to choose a very simple convex set. So I'm just going to choose the ball of radius r around the origin. It's probably like the simplest set you can think of that's convex. And we're just going to try to minimize a function f over this ball. So if you want to do this, you need to know a little more about the function. In particular, the complexity of the problem will depend on how quickly the function can change in a small interval. So the function changes an arbitrarily large amount in an arbitrarily small interval, then you're not going to be able to find a minimum. So we need some guarantee about how quickly it changes. And the standard way to ask for such a guarantee is to ask for the function to be Lipschitz. And what that means is there's some constant g for which this relationship holds. This relationship just expresses the fact that if you move a certain amount in the domain, then you don't move more than g times that amount in the range. Okay, so now that I've defined this, I can say what our basic problem is. Our problem is constrained convex optimization. So you have a constraint set, which is the ball of radius r. You have some function, which is Lipschitz with Lipschitz constant g. And x star is the true minimizer. It's the point inside the ball of radius r where the function f achieves its minimum value. And you don't need to find x star exactly. You just need to find an epsilon approximation. So it's fine if you output some other point x. The guarantee we require is that f of x minus f of x star is less than epsilon. Okay, so that's the basic problem we're going to be considering in this talk. Are there any questions at this point, or should I?
There is a question, Robin, by Nishit. Let me read it out. If not, what does it mean that gradient descent can solve a problem optimally? In general, convex optimization, it's not very clear what it means to solve a problem optimally, as we always find approximate solutions. And runtime depends on approximation guarantees.
Okay, yeah, that's a great question. So I'll say in a couple of slides exactly what I mean. But so formally, the problem will have a bunch of parameters like the Lipschitz constant and the radius r and epsilon and the dimension. And what I'll mean by optimal is I'll mean optimal dependence on all of these parameters. But I need to formalize the problem a little more before I can explain what that means. Okay, so yes, let's go to the next slide. Okay, so I need to formalize this problem. And what's the part of the problem that needs formalization is I haven't told you how the input is represented. So for a computational problem, this is very important. Like the complexity of the problem will often depend on how the input is represented. And what I'm going to do here is I'm going to talk about a black box representation. And what this means is you have, let's start with what's called zeroth order convex optimization. Here you have a black box that can compute the function f for you on any input of your choice. This is not the setting we're working in because gradient descent doesn't just use the function value, it also needs the gradient. So this is called first order black box convex optimization. So here you have access to both the function and the gradient of the function, which means you can submit to this black box an input x and ask the black box for either f of x or grad f of x. Maybe this is a good point to say that if the function is not differentiable, technically the gradient may not exist, but what you want is something called the subgradient. And I'll say a little bit about it later, but for now, to understand the problem, just think of it as the gradient, and it's totally fine. And the phrase black box refers to the fact that you can only query this box at inputs of your choice, you don't actually know anything about the function other than this query access to this black box. So you don't know what the function looks like, or you don't have some global structural understanding of f other than our assumption, which is that it's G Lipschitz. Okay, now that I've specified the problem, the input formally, I can now tell you the formal version of this problem. So it's first order black box convex optimization. So the same setting as before, same parameters as before. And the goal is to solve this problem while minimizing the number of evaluations of f and grad f, or number of queries to this black box. Now that's the formal way of saying what we're trying to do. Okay, good. And right, so now I can get to exactly what I mean by optimal. So this problem depends on 4 parameters, right? Four parameters appear in this problem: n, g, r, and epsilon. But they're not all independent parameters. Actually, there's only 2 parameters, n and gr over epsilon. And the reason there's only 2 parameters is there's some freedom in the problem, which is you can scale the input and output domains, and this doesn't really affect the problem. So you can play around with these 3 parameters, gr and epsilon, and trade them off against each other. So really, it's just one parameter, gr over epsilon. Or in other words, you can just fix g and r to be 1 without loss of generality, and just think of there being 2 parameters, n and epsilon. Okay, so there's 2 parameters, n and epsilon, basically. And now you can ask, what are the best classical algorithms for this problem? And it turns out there's 2 different best classical algorithms. And one is gradient descent, which has complexity gr over epsilon squared. And this is the kind of algorithms I'm going to be talking about today. And these are called dimension-independent algorithms because, as you can notice, the dimension n doesn't appear in the complexity. Whereas this other class of algorithms, which are dimension-dependent algorithms, n does appear in the complexity, but I'm not really going to talk about those algorithms, but I'm just mentioning it now because people often ask about, because they're familiar with the ellipsoid algorithm, how does that work? But I'm kind of thinking of the situation where n is very large, so you don't want dependence on n. And in this case, it turns out that gradient descent is the optimal algorithm. And what that means is you can prove a lower bound, that you need gr over epsilon squared queries. Any classical algorithm must make so many queries. Okay, any questions at this point? Okay, good. Right, so as I said, gradient descent solves this problem that I formally stated with gr over epsilon squared queries. And just to be like super explicit, I'll tell you what the algorithm is in this scenario. What you'll do is you're minimizing over this ball of radius r. You don't know anything about where the minimum is, so you might as well start at the origin, which is the center of this ball. And then you do the following iteration t times. You take the point that you're at, xi, you compute the gradient at that point, and you subtract eta times the gradient from your point xi. The step size eta is chosen to be epsilon. This is your accuracy parameter. And finally, this step might take you outside the ball of radius r, which is bad because you're trying to find the minimum inside the ball of radius r. So then you just project yourself back to the ball of radius r. That's very easy to do. And then finally, you just output the average of all of your iterates so far. So this is one version of gradient descent that works, and it indeed has the correctness guarantee, which I'm not going to prove, but it's actually pretty easy to establish. The correctness guarantee is just that the output of this algorithm is f of x minus f of x star is less than epsilon. And furthermore, the optimality claim is the following, that any randomized algorithm that's dimension independent that solves this problem must make gr over epsilon squared queries to these oracles. Okay, good. Any questions?
So there's a remark by Nishit that these are number of iterations, right? Not the like gradient may need some time to compute as well.
These are number of queries made to the oracles f and grad f. So that is the complexity measure, number of queries.
Yeah.
So
thanks.
Can I ask another quick clarification there? So you claim that the gradient descent was optimal, but isn't it actually the Nesterov momentum method that's optimal?
No, not in this setting. So in this setting, all I've done is I've assumed that the function is bounded Lipschitz constant. And in this case, this gradient descent algorithm, this specific algorithm that's on this slide, is the optimal algorithm. The setting that you're thinking of is where you assume that the function is smooth, like the first derivative is also bounded. And that's when the Nestor momentum algorithm is optimal.
Okay, thanks.
Yeah, any other questions? Okay, good. So yeah, so we have this problem. It's totally formally stated, and gradient descent is optimal for it. And I'm going to ask, well, what's the quantum query complexity of this problem, right? What's the complexity of solving this problem on a quantum computer? This is my slide about like what's the issue with gradients. Let me just skip this. It's not a big deal. Essentially, what happens is if the function is not differentiable, the gradient may not exist. So what you do is you replace the gradient with this object called the subgradient, and the subgradient is just any vector that satisfies this equation that the gradient satisfies. The subgradient may not be unique, but if the function is differentiable, the subgradient always equals the gradient, but the subgradient always exists. So all you have to do for these optimization problems is assume that when you query the black box for the gradient, you get a valid subgradient. And that's kind of how you make it work for non-differentiable functions. But it's not a big deal if you haven't seen what subgradients are before. Everything will make sense if you just take the intuition of gradients as for differentiable functions. Okay, so yeah, so now we can ask the question of can quantum computer speed up gradient descent? And as I said, this is how we're going to formalize it. We're going to say this is the problem. We're only counting the number of queries to f and grad f. Gradient descent solves this with some complexity, GR over epsilon squared, and no classical algorithm, even randomized. So note that gradient descent is a deterministic algorithm, but what I'm claiming is even randomized algorithms can't solve this problem any faster than gradient descent. So gradient descent is optimal among all classical algorithms. Can quantum computers solve this problem faster? Right, that's the question. And there's one last thing that has to be done to make this question formal quantumly, which is I have to tell you how quantum algorithms have access to f and grad f. Now, fortunately, since this is a quantum workshop, I think most people know what's going to happen over here. It's just the usual thing. You take some classical black box, you make it quantum by making it reversible and unitary. Traditionally, it's done in the setting of Boolean functions. So you have some classical black box that takes in an n-bit string x and outputs a bit f of x. This is not reversible or unitary, so you would make it into a quantum black box. And the justification for why this is reasonable is because if you had a classical algorithm or a classical circuit that did the thing on the left, then you can convert it to a quantum algorithm in a completely mechanical way that does the thing on the right, and the gate complexity will be the same. It'll use the same number of gates, so that's why it makes sense. So we do the same thing, and there's an additional wrinkle in our model is that we're dealing with real numbers. So you have to deal with that, but let's not worry about it. It's not going to matter at all. So let's forget about that. But one way to do that is you can just say that the real numbers are specified arbitrarily high precision. You can ask for whatever precision you want from the oracle, and it still counts as one query. All right, so now I've made the problem well-defined quantumly, and let me go back to what are we asking? We're asking, can quantum algorithms solve this problem faster? And we know a classical lower bound of GR over epsilon squared. So one thing to do when you're at this kind of place where you're trying to ask if quantum algorithms can solve the problem faster than classical algorithms is to take the classical hard instance, the hard instance that appears in the classical lower bound, and see if you can speed that up quantumly. Right? That's a good place to start, because you know that instance is hard. And so that's what I'm going to do. I'm going to investigate the classical randomized lower bound hard instance, and this is what it looks like. As I said before, let's just assume that G and R are 1. So there's only one parameter, epsilon. And we're working this dimension independent setting. So that means n can be arbitrarily large. So I only need n to be as large as 1 over epsilon squared. And I'm going to consider the following class of functions, fz of x, where z is an n-bit string of plus ones and minus ones. And the function is just defined as the zi xi maxed over all the indices I. And it's not easy to, it's not hard to show this is a convex function, because zi xi are linear functions and the max of convex functions is convex. And so this function is kind of interesting. So it satisfies our assumptions. Of course, it's one Lipschitz. We're trying to minimize it over the unit ball, and it turns out you can figure out what the optimal point is very easily, because what you want is you want to minimize this function. So you want this product zi xi to be negative everywhere. So you want xi to have the opposite sign of zi, and you have a constraint on the norm of x, right? Because you have to be in the unit ball. So you want to choose the furthest away x from the origin that has this property, and it turns out it's this point. And the minimum value is, well, this, whatever, minus 1 over root n. Okay, cool. And any randomized algorithm that solves this problem must make 1 over epsilon squared queries. That's the claim. I'm not going to prove it, but it's actually not very hard to prove. Essentially, the intuition is that every query you make only reveals one ZI to you, and you really need to figure out all the ZIs to find this optimal point. And so you really need to make like n-ish queries, and n is 1 over epsilon squared. Okay, so that's our classical lower bound. And as I motivated, like, we should think about, can we do better on this family of functions with a quantum algorithm? That's a good place to start. And yeah, so can we do that? It's just a recap of the previous slide. We have this family of functions, max I, zi, xi, and any randomized algorithm must make omega n queries. Can we do better than n quantumly? Okay, so to answer this question, let's just make some observations about this function first. So here's 3 very simple observations in increasing order of complexity. So the first observation is, if I query with the all ones vector, then the response from the oracle for f, like f of x is 1, if and only if one of the zi's is 1, right? Because now f of x just becomes max I zi. And zi is a plus minus 1 string. So it tells me 1 if and only if there's an index equal to 1. The second observation is, now instead of the all ones vector, if I just take the all ones vector supported on a set S, the indicator vector of some set, then I'll get back a 1 if and only if there exists an index in that set for which zi equals 1. And in other words, we're able to make queries of the following form. I can specify an arbitrary subset of my choice and ask the oracle, does z, the string z, which I'm thinking of an n-bit string, contain a +1 within this specified subset? And I'm going to call this a subset OR query. And the reason I call it that is I specify a subset, and what the oracle does, it completes the logical OR of all the bits inside that subset, where +1 is treated as a logical true. Okay, so now the problem is reduced to the fact that we have some n-bit string, or string, a plus minus 1 string of length n, and we have these subset OR queries to them, and we want to learn all of these zi's, so we want to learn the entire string. And can you do that with fewer than n queries? And it turns out that you can. This is a remarkable result of Alexander Belov's. He shows that given these subset OR queries, you can actually learn all of these zi's with high probability using only square root n quantum queries. So in fact, quantum algorithms can solve this problem faster, and there's a quadratic speedup. This classical hard family can be solved faster by quantum algorithms. Okay, that's cool. Any questions about this so far? Probably a good place to pause. Nope. Okay, good. So, right. So yeah. So now we're at a pretty interesting point, right? So when we, this is kind of a chronological story also of how we did this research. So we also got to this point at some point in our research, and then we were like, so there is a hard family of functions that appears in the classical lower bound, which can be solved quadratically faster quantumly. So what's going on, right? Like, can quantum computers always give a quadratic speedup, or like, was it just a coincidence? That's kind of like the obvious thing you would ask at this point. Like, was this just some special property of this family of functions, or is it just like a general phenomenon that quantum computers exhibit? And the main result is that, well, there's no quantum speedup in general. There exists a hard family, just a different hard family of functions for which even quantum algorithms must make 1 over epsilon squared queries, which is the complexity of gradient descent. So this answers the question that we sought out, our formalization of this question, which is just in the setting of first order black box convex optimization, there's no quantum speedup over gradient descent. Good, okay. So now that I still have 5 minutes, I can tell you a little bit about how the quantum lower bound works. I don't want to get into too many details, but I want to kind of roughly sketch what's the key idea. So to understand what's the key idea is, recall the classical lower bound. Your function fz of x was a max over I zi xi. And this lower bound instance doesn't work for quantum algorithms. So we're going to have to modify it in some way. So we modify it in 2 ways. So the first way is is the first term, which is I have these inner products of vi and x. And let me explain what's going on over there. So zixi is just the ith bit of z multiplied with the ith bit of x. But you can also view this as an inner product between two vectors in Rn. The first vector is x itself, and the other vector is the ith basis vector multiplied with a sign. So it's zi ei, where ei is the ith basis vector. And so now what's happening is it's a max over n things, and each of these n things is an inner product of our input vector x with one of the basis vectors with a sign in front of it. So plus or minus a basis vector, and these basis vectors are all orthogonal to each other. So there's something going on in this function which privileges the standard basis, the computational basis, because I'm using these EIs as my vectors. So to make the problem more quantum, make the instance more quantum, we choose a random set of orthonormal vectors now. So v1 to vk they're still orthonormal. They're just not the standard basis vectors. They're just some random collection of vectors. So that's the first change we make to go from the classical lower bound to the quantum.
So sorry, why did you change k to n here? Or n to k?
Yeah, I'm gonna use fewer vectors than the dimension this time. So because we don't know how to make the lower bounds go through with k equal to n. So I'll use in other words, I'm going to need a larger dimension n to prove the same lower bound in the quantum case than in the classical case. So that's the first change that we make. We make this zixi become inner products. And the second one is we add a penalty term that's proportional to the index I. And so there's a lot of stuff going on in the second term, but just forget about everything there except the minus I. So what's happening here is you're taking a maximum of a bunch of things, but the first term gets a -1, the second term gets a -2, the third term gets a -3, and so on. So each term is being penalized in a different way. And the reason we're doing this, the intuition is that if I pick a random vector x, so just pick an x uniformly at random in the unit ball, with this orthonormal set of vectors, it'll roughly have the same inner product. The inner product will be roughly 1 over square root of the dimension. And if all of these vectors have roughly the same inner product, we want to enforce an ordering on them. We want to say that if they're all roughly the same, then because we're penalizing all of the vectors much more than we're penalizing the first vector, you should output the first vector. The other stuff that's going on over there, this gamma and stuff, that's kind of setting the size of the penalty. So I want the penalty to be large enough that it's actually comparable to this 1 over square root of the dimension variance that'll happen in these different VIX inner products. Yeah, maybe that's all I wanted to say about how we change the function. And then what's the intuition for how the lower bound works is, as I said, if you query this function on a random x, there's a very good chance that the function is actually maximized on the first term. So this is a max of k things, v1x, v2x, v3x, and so on. There's a very good chance, like a very good meaning like 1 minus 1 over polynomial, chance that the function is maximized on the first term. So the function looks like v1 inner product x at the point you've queried. And so you get this value, v1 inner product x, if you query the function. And if you query the gradient, what's the gradient of v1 inner product x? v1 inner product x is just a linear function. The gradient is v1. So you learn the first vector v1. So the intuition is that the first query only reveals the vector v1 to you. The second query can at best reveal v2 to you if you query it with a random vector on the whole space minus v1. So now remove v1 from your space and now pick a random vector. Then you'll get v2, and you keep doing this and you get v3 and so on. And the lower bound idea is that this is every algorithm only learns vectors in this order. You must first learn v1, then you learn v2, then you learn v3, and so on. But you must know all k vectors to get the final answer. So you must make k queries. That's kind of the high level overview of how this proof works. So it's very analogous actually to the classical lower bound, at least in terms of high level ideas. Making it rigorous is somewhat different quantumly than classically. So quantumly we have to use the hybrid argument. That's like the lower bound workhorse. All right, so okay, I'm at the end of my time. So let me conclude with some open problems. So in one sense, the result is somewhat disappointing. There's no quantum speedup in the setting of first order convex optimization. But there is a speedup over this very special class of functions, the ones that appear in this randomized lower bound that I talked about. So one question is, well, is there a more interesting class of functions for which there's a quantum speedup? some class of functions that actually appears in practice or that people care about. Another interesting question that I didn't talk about at all, because I was considering this high dimensional setting where n was very large, but let's think about the setting where n is not very large, and let's think about the setting where n is actually kind of small compared to gr or epsilon. So that means you want a very precise estimate. Then you're not going to use gradient descent. You would rather use the other type of algorithm, this ellipsoid algorithm type of algorithm, which has complexity essentially linear in n. And there the interesting question is, what's the best quantum algorithm for that setting? And all we can say right now is that there's a lower bound of root n, but there's a gap between this root n and n. And this lower bound of root n was also only recently shown in this paper of Van Apeldoorn, Gillian, Gribling, de Wolf, and also in an independent paper of Chakraborty, Childs, Lee, and Wu from last year. And yeah, in a more open-ended direction, you can ask, well, what about other natural settings in convex optimization? Like, what about minimizing smooth functions, right? There was a question earlier about, like, what about Nesterov's accelerated momentum method? That's the optimal algorithm for the setting of smooth convex function optimization. Can you do any better than classical algorithms in that setting? In that specific setting, actually, it turns out the answer is no. And we can show this, and we have written this up, and it should appear at some point on the archive. But you can ask many questions like this, right? What if I assume something else about the function, or you can even go out of the setting of convex optimization, right, and go to non-convex optimization. It's very hard to prove stuff there, but I'm sure there's tons of interesting questions there about, can you get quantum speedups for optimization problems? All right, so let me stop there. Thanks.
Thank you, Robin. It was a very clear talk. So now we have plenty of time for questions. So if you have a question, please type it in Q&A, chat, or speak up. So I have a question about, you say that, like you explain what is the family of functions that you work with, and I guess this K is roughly like something like order n, but not quite n or something.
No, it's a little worse than that. So for the very specific family of functions that I showed on the quantum program slide, we need n to be like k cubed. So there's a cubic gap between the dimension and the number of vectors. But we also present an alternate construction in our paper that's much more complicated. That gets n to be roughly k squared. And that's also kind of related to the second question. If we could get the dimension and k to match, then we would also resolve this low dimensional question.
Oh yeah, that's true.
Which we're not able to. We're kind of stuck roughly in place.
And you said that, so you have two different lower bounds proofs. One is with k squared, one is with k cubed.
That's right. The worst one uses the function that I talked about. So it's worse only in the sense that the dimension required for establishing the lower bound is larger. Like, it's still proving the same lower bound of 1 over epsilon squared. But the one that's worse uses this kind of intuitive function that I talked about on the previous slide, which is, it's kind of easy to see how we went from the previous function to this function. The more complicated function that gets the better dependence on dimension is, I want to say it's a crazy complicated function, but it appears in a classical lower bound. So people have studied the complexity of gradient descent in the classical randomized setting, but with parallel queries to the oracle. So now what happens is, in every round, you can make polynomially many queries to the oracle, and you're only counting the number of rounds needed. And so this is a much harder setting to prove lower bounds in, right? Because you're just counting the number of rounds, and you can make many queries in each round. And for proving lower bounds in that setting, so there are better algorithms known in that setting. You can improve on gradient descent, but in that setting, people have developed a very hard class of functions to use for proving these lower bounds, and that's the class we have to borrow to make our better lower bound. But that's kind of much more much more painful. So if you just care about the 1 over epsilon squared lower bound, you don't need to read that part of our paper. So it's kind of separated out into first the easy lower bound and then the harder lower bound.
But in both of these cases, the proof technique that uses this hybrid method, which was originally used for proving the optimality over search.
Yeah. The quantum part is almost identical in both. Like, in fact, there's a way to view the proof in a very black box way where like all that's done is we just need to establish certain properties of this class of functions and like plug into our quantum proof, and the same proof will be for either class. It's just that this family of functions is pretty complicated, and the properties that needs to be established are more complicated.
So does the classical lower bound also use hybrid method for the original function that you showed?
No, well, because you see, classically, like the way you would argue this is you would just condition on events. Right? So I'm saying that you do something, and with very high probability, 1 minus 1 over poly n, you only learn let's say one bit of information. Then you'll say like, well, in that 1 over poly n chance where you learn more than one bit, we just abort or whatever. Let's say the classical algorithm just wins, and we'll just condition on that happening. But like we're conditioning on a very unlikely event, on a very likely event. So even at the end of the day, most likely you haven't conditioned on anything, and so you use this style of argument classically, which makes the classical algorithm very straightforward. But yeah, maybe you can think of the hybrid argument as some kind of quantum way of doing this.
I see. Cool.
I'm not sure how much you would be like. I mean, you said it's a preliminary work, but if you can say a little bit more about this, you said that you have something which is a follow-up work to this, and it's about optimizing like smooth functions that would allow Nesterov's accelerated method, and you show that like in that generality you cannot get a quantum speed up. Is that the thing that you said?
That's right. So the thing we're able to prove is okay. So what's the smooth setting? So actually, there's, depending on what kind of assumption you make on the function, there's infinitely many different smooth settings. The basic one is you would assume that instead of assuming that the function is Lipschitz, you'll assume the gradient of the function is Lipschitz. So this we can call like the I don't know, p equal to 1 setting. But then you could also assume that like the first p derivatives basically are Lipschitz, that you can stop wherever you want. And for each value of p, there's a different optimal classical algorithm. For p equal to 1, where you assume just the gradient is Lipschitz, the optimal algorithm is this Nesterov accelerated gradient descent. Then for p equal to 2, it's something else. I forget what it's called. Maybe it's called like accelerated Taylor descent. Or whatever. For p equal to 3, there's a different algorithm that's not. Basically, there's a recipe for constructing these algorithms. And for all p, you can show that this family of algorithms is optimal. And the complexity basically goes like, it's like 1 over epsilon to some power, and the power is a function of p. And the power is something like 2 over 3p plus 1 or something. And what you can show is classically, at least among deterministic algorithms, this family of algorithms is optimal. So until our work, it was actually not known that even for randomized algorithms, the complexity was not known. So in this follow-up work that's still not available yet, we show that for both randomized and quantum algorithms, and for every value of p, the deterministic algorithm is actually optimal. So there's no quantum speedup. In fact, there's no randomized speedup either for all values of p. So it's not only does it establish that this accelerated gradient descent of Nesterov is optimal, but like the full family is actually optimal, both classically and quantumly. So in that case, in that result, we're actually able to prove a new result even classically, because the randomized lower bound was not known. And
for any value of p, was it known for like p to +1 or even not for that?
No, okay, no, it was known that Nesterov's accelerated gradient descent is optimal classically, even for randomized algorithms. That's right. I think that was known, but the higher valued versions were not were not known even classically. And yeah, the nice thing is our construction just kind of gives it to you for all P for both classical and quantum. And yeah, so somehow thinking about quantum forces you to try certain kinds of proof strategies. It's like you're trying to prove this. If you're trying to prove the randomized lower bound, you would have far more proof strategies at your disposal. And because we're doing quantum and we only know one proof strategy, which is this hybrid argument, we had to find a family of functions that makes that happen. But once we found that, then it just worked and gives you a classical lower bound for free. So this is one of those cases where having fewer options is better.
Very nice. It's one more example than like classical computer science can benefit from quantum.
Right. I mean, although you can take our construction and like remove all the hybrid method stuff. Like once you've found the family of functions, then you don't need to talk about quantum anymore. It was just that the motivation to find this exact family of all of these properties. We have like a list of 3 properties that need to be satisfied. That was because our hands were tied by the hybrid method.
So would it extend also straightforwardly to the more general projected gradient descent to any kinds of convex constraints?
Yeah, this I'm not totally sure. Yeah, if you have different convex, if your convex set is not a ball of some radius. Yeah, our lower bounds are pretty specific to this setting, and I suspect I'm not sure actually. They may not hold. In fact, the optimal algorithms in these other settings might also not be the same optimal algorithms in this setting. Yeah, that's a good question. I'd have to think about it some more. But
isn't the projected gradient descent also optimal in the general setup with convex constraint?
Is that right?
I mean, without smoothness and strong convexity and so on and so forth, where you can do acceleration.
Yeah, I'm not actually sure if projected gradient descent is optimal even for other things other than balls. Like if I had like the unit L infinity ball or something, would you still use projected gradient descent, or would you use a different algorithm?
All right. I would say that in the interest of time and keeping up the schedule, let's maybe take this discussion offline. And let's thank Romy once again for this very nice talk. And now it's time